For lesson 5-6, we're looking at inverse relationships and their functions. So it is important to note what a function actually is. You might recall from a previous course that when something is a function, you put in or substitute in an x value and a specific y value will come out of the function. So if we had an equation, you could say plug in x is -2 and out comes the y value of 1. When it's a function, you put in an x value of -2 and you only get this y value of 1. You don't have any question. So if I put in -1, I get out 4. If I put in 0, I get out 3. There's no other answer that could come out. A couple terms that they're reviewing here. An independent variable is the input, the x value. So you input or plug in that -2. We call that the independent variable. That's what you choose to plug in. The output is dependent upon what equation or function you're using, or maybe what pattern. So these are all our dependent variables because they are dependent upon what we put into the equation. So when they ask us on example 1, what is the inverse of the relation represented in the table, we look at all of our x, y values, and we again can note that this is a function because each x value is different, and when we plug it in, we only get out one y value. When it comes to finding the inverse relation, note our vocabulary over here says that the roles of the variables are reversed. That means, so when you're doing this actually in a table, what's going to happen is your variables are going to reverse or flip-flop. So instead of -2, 1, we're going to write x is the 1 now and y is the -2. Or here, 4 will be the x, y will be the -1, and so on. The math of it isn't too tricky. We basically will just switch our x and y values. So finding the inverse variables of an equation or a table are not tricky. You can just flip-flop the x and y values. But what happens is there are two main concerns here. Look at our new values here, specifically that I'm circling, and I'll put these in here. When you input an x of 1, you get out a value of -2. But they're also saying when you input a value of 1, you get out a value of 1. This is where that confusion happens. This makes our inverse relation not a function. Each input of 1 gives a different output. So since that is not a function, we have an inverse relation, but it would not create a function. So the table part, say on the triad, is super simple. If you have a function x, y, we notice that there's no repeated x value, so we don't have to worry about same x value giving a different y value. But when I flip-flop them all and I enter them as such, I have to go back through and double check if any inputs are repeated. Notice how all of these are unique, so I don't have to worry. Like on the last problem, when I had 1s inputted for x twice there, and they gave different y values. So this one, we would say, it says identify the inverse. This is our inverse relation. And is it a function? Yes, because each x value is unique. So there's no two x values the same, therefore there can't be a place of concern where the same x value gives a different y value. Now when we look at an equation in example 2, we're no longer looking at a table of values. We're looking at a graph, if you will. So let's look at the inverse relation of f algebraically. We can rewrite f of x equals x squared as y equals x squared. We are going to flip-flop or switch our x and y variables. Remember, that's what we did in the table. We switched the x's and the y's. By doing that, then, to find the inverse function, we're going to get y alone by itself. So canceling out that y squared, we square rooted. Now remember, when you take the square root of both sides, we're going to have a y left here, and we're going to put plus or minus root x. So we would say our inverse function is this plus or minus the root x. I should note that on this page before, when we first got our vocab of what an inverse function is, it's noted as f to the -1 of x. And so we note that as f inverse, and we're going to write that again here as f inverse of x equals plus or minus the square root of x. So that notation is important. Oftentimes, we're probably going to refer to it as just the square root of x, but let's talk about this plus minus. When we look at the graph over here, x squared is graphed in blue. Our y values rather, so our range, the range of f is that y must be greater than or equal to 0. So remember when the x's and the y's change, that means our inverse function relation must have an x that must be greater than or equal to 0, and that is the case. Look at our inverse function here, the plus square root of x and the minus square root of x. It starts at 0 and goes to infinity. Now, we know that our inverse function here, if we look at plus root x and minus root x, it looks like that sideways parabola. We have a problem here because let's say you plugged in 4, for example, 4 up here. If I plug in 4, the square root of 4 is 2, but the square root of 4 could also be negative 2. If that was a table, when we plugged in 4, we'd get 2 or negative 2. This is not a function. That's because any input here, when we put in an x value along the way, it has a positive y value there and a negative y value there. So while we found an inverse relation of the function in plus or minus root x, it actually would not be a function. We'd have to restrict our domain. So if we were only to look at this right-hand part of the equation of x squared, we would just be focusing then on this top part. So if we restrict our domain, let's say our domain for our blue graph, and I'll write in blue here for that. If we restrict our domain where x has to be greater than or equal to 0, so just this right part, then our inverse function, that's on our function, then our inverse function in orange will have a range such that the y must be greater than or equal to 0. Because our x's and our y's switch, we'd only be using that top one. If we were only using the top part of the graph, we would be good to go with the function idea because we would only be using 4, 2 as a point, not 4, negative 2. So keep in mind when you flip-flop the x's and y's to find your inverse, it doesn't always mean that that is an inverse function. On the try it, if we have y equals 2x plus 1, to find your inverse, you start by switching your x's and y's in their location, and then rearrange the equation to get y alone. So I would divide by 2 here on both sides, and my inverse function would be x minus 1 over 2. Now, if we graph this, this is going to be another line. We're not going to have any concern. So it will be a function, and we would have every x going only to a specific y value. For example 3, it gets into kind of what I've already talked about, how you might have to restrict the domain. If you look at when x is 2 and 2 squared is 4 and negative 2 squared is 4, these are our problem points. When we plug in these values, we get the same y value. So when you do the inverse over here, we would get 4, 2, and 4, negative 2. That would not let it be a function. So we definitely restrict our domain, just like we talked there, only using that first part. We would say x would have to be greater than or equal to 0. That means then when we do the inverse function, we're only using y is greater than or equal to 0, and we will be okay. We will actually have a function. Check your answer key packet for the answers to the fill in the blank, but we're definitely only looking for eliminating those xy switches that would possibly cause same entries in the x value on the inverse to give different y values. I'll look at one of these triads here. Think of x squared minus 9. That's like a parabola that hits down here at negative 9 on the y-axis. So if I have x squared minus 9, they say, where should we restrict the domain? Well, think about it. If you plugged in this x value here and the opposite of that x value, you'd get 2 different y values. That's where we cause the problem. So if we restrict only for part of this graph, we would cut it off here. We'd want our domain only to be from x is greater than or equal to 0. So we only have each x giving a y value and no y values repeated. So by knowing that I'm only using these x values from 0 on, I can then follow that idea where if I want to find the inverse of a function, I write it out with my x and y, Then I switch my x and y values, so I'll have x equals y squared minus 9. Add 9 to both sides. I want to get my y alone, so I would have x plus 9 equals y squared, and then I'm going to square root both sides. To get my y alone, x plus 9 square rooted will be our y. Our inverse, we would write it f inverse of x would be the square root of x plus 9. And we know that that's going to be a function because we've restricted our domain. So by restricting our domain to only be 0, we don't have any duplicates, x value inputs that give 2 y values for just that top part of the square root function. Example 4 kind of puts it all together here. We see the square root of x minus 2. It should look familiar from our graphing in section 5.3. It's shifted to the right too. Our domain, we know all the x values go from x is greater than or equal to 2. Therefore, that's going to be our range. So our range then, when it switches, now we will say our y values will be greater than or equal to 2, because remember the x and the y switch places. Whereas our range, it starts from 0 to infinity, so we would say our range would be y is greater than or equal to 0. That'll be our new domain, x is greater than or equal to 0. If we look at this graph, here is our original f function, here is our inverse function. If we were going to actually solve for the inverse function, I would need to switch my x's and y's and then square both sides to get my square root to cancel. So x squared equals y minus 2. Then I would add 2 to both sides and have y equals x squared plus 2. And of course, using our fancy inverse notation, it would look like this, which if we go back up here in red, hey look, it starts at 2, it's a parabola, and that's its inverse. One thing to point out as well, if you found the inverse correctly, a regular function and its inverse should be reflected over this line y equals x. So it kind of looks like a mirror there. That will happen. You can look at part B, check out that line mirror there. These functions definitely flip over each other. Your inverse function here for part B, y equals negative third root of 4x. You can see why we needed to have all that practice earlier on getting cube roots out of here, because now I have to switch my x's and y's, so negative third root of 4y. I got to get that y out of there. I'm going to start by dividing by negative 1 to get that negative sign gone. So that'll be negative x equals the third root of 4y. To cancel out that third root, I'm going to take it to the third power on both sides. Now a negative times a negative times a negative keeps that negative out there with my third power, and this will be my 4y. And to get y alone, I will divide by 4 on both sides. So my inverse function will be f inverse of x is negative x to the third all over 4. And that is what is graphed here in orange.